in this lesson, we're going to go back and revisit the half period of motion, look at a summary of the half period of motion, but in more detail mathematically. So to remind us of our mathematics, we are looking at the charge on the capacitor, right, given by Qmax cosine omega t, such that when at time t equals 0, the switch is closed, charge will begin to flow. The charge on the capacitor is given by this expression, and then of course the voltage across the capacitor is V equals Q on C. So the Q that we have over here is the Q that we would plug into our Q on C equation, right, to get the voltage across the capacitor as well. And of course we mathematically can generate the current by taking the derivative dq dt. We can get di dt by taking the derivative again, and of course our di dt is important because that allows us to also determine the voltage on the inductor as a mathematical expression. We have L di dt, and we're going to use our di dt here to get our expression. Now, there's a very important consideration for our LC circuit and our oscillating circuit. So please make sure you get down especially this first bit here, the fact that same color, same voltage. At time t equals 0, when we close the switch, we are going to have same color, right? Same voltage here, same color, same voltage here. So in a sense, we can think of them as being in parallel. Also, please make sure you get in that this is not a grounded circuit. So if it was grounded, it wouldn't allow for the oscillation. So we are having this oscillation back and forth. But notice we also have a single loop circuit. So we kind of have both a series and parallel situation going on here at the same time, but we don't really have the same type of circuit. So you don't want to think of it as we were thinking of our old circuits, but we do need to know that the capacitor and the inductor will always have the same voltage across them, and they will always share the same current. So at time t equals 0, when the capacitor begins the oscillation, the charge begins to flow, at that point in time, we have the maximum charge on the capacitor, Qmax. We have the maximum voltage across the capacitor, right? Qmax on C, and remember that will be equal to the maximum voltage across the inductor. Those two will be the same, right? Same color, same voltage. So we know that Q on C has to equal L omega squared Q, and if you set those equal, you will see, omega equals the square root of 1 on LC. So we are being perfectly consistent. At time t equals 0, of course, there is going to be no current at that instant in time. That's where the inductor is going to choke off the current, and no current through both. So kind of an interesting situation. Hopefully that makes sense. Well, how about a quarter of the way through the oscillation? Well, if you're a quarter of the way through the oscillation, then omega t is going to be given by omega is always 2 pi on the period, and we're going to simply plug in that t equals capital period on 4. Since omega always equals 2 pi on t, we lose the t. So in terms of our angular value to plug into our equations, we're at the 90-degree point. So hopefully that makes sense. 90 degrees is 1/4 of our 360. So we would simply plug the 90 degrees back into our Q equation, the 90 degrees back into our current equation, and the 90 degrees back into our di dt equation to get, of course, at this point in time, there is no charge on the capacitor. We have our maximum speed, our maximum current. Remember, that would be the maximum speed pushing the paddle wheel. We have our maximum current flowing through the circuit. Our time rate of change is 0, and of course that makes sense to us because Same color, same voltage, they have to have the same voltage across each of them. And this would also be the current that we would be saying is flowing through the circuit anywhere in the circuit. So the final thing we are going to look at for our half period of motion is when we are at capital T on 2, so omega always equals, right? 2 pi on the period, omega equals 2 pi f, frequency is 1 on period. The time we're plugging in is half the period, so we lose the t. So we are at 180 degrees, right? We're halfway through our cycle. We plug in 180 degrees. Our Q is now negative Q max. Polarity is reversed. Our current is 0. The current is 0 everywhere in the circuit. Capacitor, inductor, everywhere. Our di dt is now max, right? And the polarity has been reversed, so the voltage across the inductor and the voltage across the capacitor are both back to their maximum value. So let me zoom back out here. So if you want to pause your video, I'll get rid of some of my comment points. You can pause the video if you would like to make sure you have all of your annotations down. And we have gone through, at this point, a complete mathematical explanation of the basic functioning of an LC oscillator, the application to radio frequency circuits, and using it would introduce AC circuit theory and goes beyond the scope of this course, but hopefully we have a good understanding of the basics for the LC oscillator as a resonator able to oscillate back and forth at the resonant frequencies given by whatever L or C that we choose.